Okay, now we're starting chapter 10, which is looking at the shapes that molecules form in three-dimensional space, and we call that molecular geometry. And basically, the shape of these molecules is governed by energy. The lowest energy state is the one in which the repulsions between bonding and lone pairs of bonding electrons and lone pairs of electrons are minimized. So this results in the lowest potential energy. We're going to look at three bonding theories, two of which explain or support Lewis structures that we covered in chapter 9, and one addresses the magnetism of some molecules that's been observed experimentally. So we're going to start with valence shell electron pair repulsion. And basically, this theory rationalizes the molecular geometry on a basis of minimizing those electron repulsions between valence electrons around the central atom. In other words, the electron pairs are oriented around the central atom, so to be as far away from each other as possible, thus adopting the maximum bond angle. So we'll be looking at the bond angles associated with these geometries as well. The first geometry that we're going to look at, and I'm going to go through these with the PowerPoint slides. However, I do have a worksheet that hopefully you will work with me on after we cover the geometries. So we're going to look at the class, which is going to be represented by a letter A for the central atom and a letter B for what I call the terminal atoms, or those atoms that surround the central atom and are bonded to it. Okay. We will be counting the number of atoms bonded to the central atom, as well as lone pairs, if there are any. And in the AB2 class, we do not have any lone pairs of electrons. We're also going to be looking at electron geometry, or the arrangement of the electron pairs around that central atom, and finally the molecular geometry. Now, I'm going to say right here, if there are no lone pairs on that central atom, electron geometry and molecular geometry will be the same. Okay. So in this case, we have two B atoms bonded to the central atom, and in order to them to be as far away from one another as possible, there is the formation of a 180-degree bond angle, and both electron and molecular geometries are linear. Some examples, I'm going to flip over here, or one example to begin with is beryllium chloride. Remember that beryllium is an element that does not obey the octet rule. It has only two valence electrons and forms only two bonds, so it's satisfied with 4 electrons total. Some other examples of linear molecules that you're familiar with, or may be familiar with, we also have, let's go with black, BeCl2, carbon dioxide. Remember, we've drawn that in chapter 9. It's a linear molecule. CS2 is another example, just substituting the sulfur atoms for those oxygen atoms. The next, sorry about that. The next class that we're going to look at is AB3, where we have 3 atoms bonded to that central atom. still zero lone pairs. And this arrangement of the electron pairs around the central atom is trigonoplanar. So this adopts a bond angle of 120 degrees. And you are responsible for these bond angles. Again, there are no lone pairs on that central atom, so the molecular geometry is also trigonoplanar. Now, when we do introduce lone pairs on the central atom, electron geometry will remain the same as we were discussing here. However, the molecular geometry is going to change. Okay. Example, BF3. This was probably an example that I used in lecture, actually face-to-face, before our break. We also, I believe, looked at BH3. So most of the atoms that are going to bond with boron are going to be elements that only form one bond. Some other structures we've looked at that also have this trigonoplanar geometry are two of our polyatomic ions, nitrate and carbonate. Also, sulfur trioxide. Next up, AB4. So once again, we have 4 terminal atoms, or 4 atoms bonded to that central atom. We still don't have any lone pairs. Oops. What's going on here? Okay, I think we're good. So this structure is referred to as tetrahedral. Often when we draw a tetrahedral structure, well, I'll show you on the next page. Hold off on that for a minute. Bond angles here are 109.5 degrees, and that is the same for the molecular geometry. So this is going to end, the next slide is going to end our introduction to the most basic geometries, and we'll have another video that I'll make shortly to cover more geometries. Methane, or CH3. Oops, where's my pen? Sorry, CH4. Well, I made a mess of that. Bear with me, please. Okay, CH4. Notice that these are not, and we might have drawn this molecule this way when we drew Lewis structures. This molecule looks flat. It is not. It has a shape in 3-dimensional space, and it is tetrahedral. There are many examples of this type of tetrahedral structure. Our only positive polyatomic ion that we looked at, the ammonium ion, has this structure. PO4 3-, another one of our polyatomics, but there are a multitude of molecules that will form that tetrahedral geometry. So look for the next video coming soon.